Bismillahirrahmanirrahim. Professor Avery Broderick, Faizan, distinguished guests, ladies and gentlemen, good afternoon. It is a pleasure to welcome you all here to the Ismaili Centre Toronto for what I know will be a very exciting journey into outer space. Ismaili Centre Toronto is one of 6 global centers and is a space for social and cultural gatherings, intellectual engagement and reflection, as well as spiritual contemplation. In addition to hosting cultural and artistic performances, all Ismaili centers host lectures, conversations, and symposia throughout the year, which bring together thought leaders to foster a greater understanding of current critical issues. These programs encourage exchange and mutual understanding between diverse peoples, communities, and faiths while broadening intellectual horizons. Today's lecture, in keeping with the core values woven into the very fabric of the Ismaili centers around the world, seeks to inspire and challenge us to see the world anew and to share with us the excitement of discovery at the very edge of human understanding. We hope that this in turn can spark the imagination of the next generation of explorers and innovators. I will now ask our host, Faizan, to introduce our speaker. But before I invite him to come to the stage, let me tell you something about our host himself. Faizan is an aerospace engineer in the Mission Systems Department at McDonnell, Detweiler and Associates. He has been working on the research and development of autonomous systems for planetary exploration missions. Faizan is leading the Lunar Surface Mobility Program at MDA, where he is developing rovers for the Canadian Space Agency to support manned and unmanned exploration missions to the moon. Faizan is also developing the mobility system for the Mars Sample Fetch rover, which is part of the Mars Sample Return mission. This program is one where space agencies from around the world are collaborating to execute the first mission to obtain Martian samples and bring them back to Earth. Please join me in welcoming Faizan to the podium. Thank you.
Thank you so much for those kind words, Zaida. It is my great honor to welcome Dr. Avery Broderick, who is an associate professor in the Department of Physics and Astronomy at the University of Waterloo and an associate faculty member at the Perimeter Institute of Theoretical Physics. Dr. Broderick's work focuses on the physics of black holes and their observable characteristics. Black holes are localized regions where strong gravitational forces dominate, from the dynamics of orbiting material to the shape of the fabric of space-time itself. Dr. Broderick's works on scales spanning from horizons to cosmos, tied together by the unique physical conditions near black hole horizons. As member of the Event Horizon Telescope collaboration, Dr. Broderick participates in the creation and interpretation of the first horizon-resolving images of black holes. His team was able to obtain an image of the black hole at the center of galaxy M87, outlined by gaseous emissions swirling under the influence of presidingly strong gravitational pull. We are very excited to have Dr. Avery Broderick in our midst this afternoon. He will share with us how a global collaboration of astronomers, physicists, and engineers traveled to the ends of the world to synthesize a telescope that was able to take the first image ever taken of a black hole. Please join me in welcoming Dr. Avery Broderick.
Thank you. Good afternoon. It is a pleasure to be here today with all of you. And before we look forward, though, I want to take us back, because this is an important centenary in the annals of modern physics. In fact, one of the most important centenaries in modern physics. Because 100 years ago, astronomers, physicists, and engineers traveled to the ends of the Earth to put our vision of the cosmos to the test and fundamentally changed how we viewed gravity, and how we viewed the universe about us. And you might have heard of Sir Arthur Eddington's expeditions to Sobral and Principe, but you have undoubtedly heard of the consequence. Because in 1919, Albert Einstein, while being a central figure in physics departments, was an as yet unknown quantity. That is, he had not become Einstein the icon, the bobblehead doll. Okay? By 1919, he had already had his annus mirabilis. He had already proven the need for quantum mechanics. He had already proven the existence of atoms. And he had already dethroned time so that each of us have our own master. But he had grander ambitions. And the sheer chutzpah it can't be understated, because he sought to take on gravity. And in 1919, gravity wasn't another physical theory. It was the shining example of what physical theories could be. It was the theory that brought mathematical order to the heavens. It was predictive, quantitative, and it was the shining model. And where everyone else had seen triumph, Einstein saw only flaws. He wanted to know not only that Galileo was right, that the feather will fall at the same rate as the hammer, but he wanted to know why. Why are two of Newton's most iconic equations, F equals ma, and his equation, or his inverse square law for gravity, have the same mass? Why are they related in that way? And he also wondered how to make gravity consistent with his special theory of relativity. What was the speed of gravity? If you imagine displacing the sun, how long would it be before the Earth noticed? Would it happen instantly, like Newton said, or would it take 8 minutes? His solution was to ensconce geometry in the center of physics in a way it hadn't been since Aristotle. Geometry would become destiny. Matter would tell space how to curve, and space-time curvature would tell matter how to move. And it's really a beautiful idea. There's an aesthetic sense in physics. I can look at his equations. They embody certain degrees of symmetry that I find attractive. And shortly after positing the idea, there was already a first solution, called Schwartshield's black hole solution. Now, sometimes in academia, I feel embattled. I have conflicts with colleagues and people across the world. But here's an instance where somebody was literally doing science on the front lines of a war. World War I is where he wrote his paper on this solution, first full solution to Einstein's equations, a war that would ultimately claim his life. It wasn't until 90 years later that the two black hole problem was solved. And even then, only on very, very large computers. So that means that in 1919, Einstein's theory was in need of something very important, evidence. And this is where Eddington enters the picture, because one of the predictions of Einstein's theory is that not only apples, but also light will fall in gravitational fields. And that means if you were to look at stars behind massive objects like the sun, you would see the path their light take deflected. And this would reveal itself in a subtle shift, a mere 1/2000th of a degree shift in the location of the stars on the sky. And thus it was that Eddington went to the ends of the earth to follow the eclipse and see the subtle shift in the positions of stars near the limb of the sun. Of course, if you look at the sun directly, it's awfully bright. It's hard to see the faint stars behind it. And he did. The shift was seen, it was the right magnitude, and that's when Einstein became who he is today. Now, 100 years later, physics is in a very different situation. Gravity is no longer the shining example of what a theory could be. Even with Einstein's general theory of relativity, we know there are problems. We know that the two great pillars of modern physics, Einstein's general relativity and quantum mechanics, are inconsistent in fundamental ways. And we are searching for answers as how to bring these into concordance with each other. We're searching for ideas. And black holes are one of the handful of systems in the universe where both seem to come into play. They're a natural place to search for those clues. they're a natural place to search for deviations as the most extreme manifestation of Einstein's theory. And so once again, astronomers, physicists, and engineers travel to the ends of the earth to put gravity to the test. But this time, not observing tiny deflections of light, as Eddington had done, but observing systems where the light bends around into full orbits before traveling towards us. Ultra-strong lensing. And so I'm going to tell you a little bit today about how we did that and what we think we've learned. But first, why wasn't this done years and years ago? And the answer is a matter of size. When is something a black hole and when is it a star? It's really just a matter of how much you've compressed it, how big you've made it. The sun is about 700,000 kilometers in radius. And if I were to compress that down to the size of the Earth, quantum mechanics would enter the story, and not the thermal pressure generated by the nuclear fusion reactions occurring in the center of the sun, but by electrons not wanting to share the same space would support the object, and you'd have something we call a white dwarf. And if you were to compress that to the size of Toronto, once again, quantum mechanics would play a role. This time, not the quantum mechanics of electrons, but the quantum mechanics of neutrons, and we would have a neutron star. But if you were to compress it down to the size of Waterloo, down to 3 kilometers in radius, a large town, then there's no stopping it. There's no additional magic force. There's no quantum mechanics that's going to enter and fix things. You collapse irrevocably now to a black hole. So if you told me how massive something is, I could tell you exactly how much you need to compress it to make a black hole, how much you need to compress it before gravity takes over and runs amok. And the answer is 3 times the mass divided by the mass of the sun in kilometers. That's why the sun would make a 3-kilometer radius black hole. The Earth would make a black hole the size of a marble. I would make a very, very small black hole. I'm not collapsing anytime soon. Interestingly, the universe would make a black hole about the size of the universe. That really just means that if you want to do cosmology, you should learn about general relativity. It's not really that we're living in a black hole. But by any measure, these are small objects. Okay, this is exceedingly small in comparison to the size of the sun as we see it today. And to drive that point home, if we look at our own galaxy, we know that there is a supermassive black hole living at its heart, 4 million times as massive as the sun. And this 4 million solar mass black hole at the center of the Milky Way is observed, not directly, but by the orbits of stars going around a dark, underwhelming source. It's detectable, but it's less bright than even a modest-sized star. And we see the orbits of those stars, and you can measure the mass inside of it, just the way you'd measure the mass of the sun, and this is where 4 million comes from. And if you were to ask, how big is that size, that Schwartshield radius, in angular units as viewed from the Earth, 27,000 light years away, the answer is 1/100 millionth of a degree. Now, there are another class of black holes that are not millions of times as massive as the sun, but black holes that are the endpoints of massive star evolution. Okay, this is the way we know how to make them astrophysically. The closest one of those is 10 times closer than the one at the center of the Milky Way, but it's also 100,000 times less massive. And so that has an angular size measured in 10 trillionths of a degree. That's right out. So the only hope for actually resolving a black hole, measuring the region where photons are going to go all the way around, is to resolve this 100 millionth of a degree angular scale. And that creates, just to illustrate what that means practically, that's the same thing as reading the date on a dime on the other side of the Earth, not seeing the dime, but being able to read the date. That's equivalent to watching the hockey game on the moon and watching the puck, not standard definition. The first hockey game I saw, you just kind of figured where the puck was based on where everybody was huddling about. Could have been performance theater, but high definition, actually be able to see where the action is. And there's a fundamental problem, though, with getting those high resolutions. That's presented by something called diffraction. This is a wave optics effect. It's a consequence of the fact that light is a wave. Okay? And when it passes through finite size apertures, say the size of your telescope, those waves interfere with each other and produce interesting patterns on your detector. And you're all familiar with this, even if you don't know it. Tonight when you're driving home, hopefully you're not the driver, pay attention to the streetlights. And you'll see the streetlights all make a star. And in fact, they all make the same star. And then when you turn your head, the star is changing its orientation with your head because the star isn't in the light, it's in your pupil. It's diffraction through the pupil of your eye. You see this here, all these spiky stars on all these streetlights. This is diffraction through the aperture of the camera. And the size of that blurring of that star pattern depends on the size of the aperture, the size of your pupil here, the size of a telescope. And for the telescope I have, this is 8-meter Newtonian. Not 8 meter, I'm sorry. Oh gosh, that would be wonderful. It's an 8-inch, very different. 8-inch Newtonian. It's a circular aperture, and my star is actually a circle, a disk, and the width is lambda divided by the diameter of my telescope, so lambda by 8 inches. And so in the optical, that means that I can see something that's 600,000 microarc seconds, or about 20,000 times larger than the black hole at the center of the Milky Way. So if I wanted to try to do this with my telescope at home, my resolution would be too low by 20,000. Of course, there are bigger telescopes. There's telescopes that are planned that are even larger, and one day we hope will launch. The largest class of ground-based telescopes that we have are 10-meter telescopes. Here's Keck and the VLT. Keck sited in Hawaii, the VLT in Chile. They're both diffraction limited. You see that funny disk ring-like pattern in the images. Normally they clean those out before they release them to the public, but you can see it, and you can tell Keck doesn't have a circular mirror. It has a hexagonal mirror because its diffraction pattern is hexagonal. Of course, you could look at the mirror. Still 500 times too low resolution. Canada's a partner in the 30-meter telescope. That's not enough. We really need the 5-kilometer telescope. So achieving this high resolution, achieving an instrument or building an instrument that allows you to resolve things the size of black holes would require something vastly different than all of these. If we were to do this in the millimeter, not at optical wavelengths, but at much longer wavelengths, we might need a telescope the size of the Earth. So how would we build that? Well, why would we do it at a millimeter to begin with? There's 3 important miracles. The first is, as you go to longer and longer radio wavelengths, the atmosphere is transparent, but right around infrared and optical wavelengths, water vapor in the atmosphere, practically for us as biological beings, water in your eyeball, is a chief absorbing obscurant. It creates all kinds of problems. Okay, in fact, the visual band that you see is in the middle of a gap, is in the middle of a region where water doesn't absorb the light, and on either side, water is very good at absorbing all of the light. It's so good that we build microwaves, which zap our food and heat up water because water is absorbing the energy from the microwaves. Okay? At 1.3 millimeters, there's a hole. You can see through the water. At 0.87 millimeters, there's a hole. You can see through the water pretty well. And then after that, you're out of luck. So right around a millimeter, there's a gap. The second is the objects that we might try to look at, things like the black hole in the center of our galaxy, they're bright in the millimeter. They're not so bright at optical. They're not bright in infrared. Okay, so their peak brightness, where they're shining the best so we can see them with the highest sensitivity, happens to be right around a millimeter. And in fact, anything that's bright at shorter wavelengths is a problem because the stuff around them is going to do the same or create the same problems that water vapor in our atmosphere creates for us. The stuff around them will obscure the black hole. So there's a peak right around a millimeter where we can see down to horizons and we can see most brightly. And the third is that with a millimeter wavelength telescope the size of the Earth, we can just barely see multiple objects, the event horizons, in more than one black hole. That's that 100 millionth of a degree scale. It turns out that that diffraction limit means that at 1 millimeter wavelengths, a telescope the size of the Earth is just barely big enough. And making the Earth bigger is really, really expensive. So that's an even larger challenge. So how do you build an Earth-sized telescope? Well, what does a telescope really do? Imagine we had a mirror the size of the Earth. What it would do if it had the special parabolic shape is it would reflect incoming radio waves back to focus in phase. All the light would return to focus at exactly the right time. And at focus, you could construct an image and do your astronomy. Of course, building a mirror across the entire planet creates political problems. So instead, imagine building just pieces of it, shards of the mirror, each of which reflecting just a little piece of the light back. And then imagine not reflecting the light, but recording it to hard drives, actually measuring the incident light wave, the radio wave. And then on large computers, completing the process of propagating it back to focus and generating the image. And this is what you'd have with the Event Horizon Telescope. Now, that analogy is almost exact, but not perfect. An exact analogy would be that we really are filling in the mirror with every pair of telescopes. The distance between every two telescopes gives us a position in the mirror. And so every pair of telescopes gives us a point in the mirror, and if we wait, if we're patient, the Earth rotates, the relative position of those telescopes change as seen from our source far away, and streaks are filled in. And that's shown here on the right, where we see these mirror with these blue streaks inside. And in some sense, the Event Horizon Telescope, or a radio interferometer, is exactly something that fills in a mirror that looks like those blue streaks. It's only silvered at those positions. So the photographers are all wincing. It's almost as if I've taken your beautiful lens and I've scratched it up on those blue positions, and that's what we're so proud of. This is, nothing is free. This is difficult. It is difficult because in order to do this process, we don't actually take a picture at each of those sites. We have to record the full radio wave. Think soundtrack, not image. We need the ups and the downs of the oscillating radio wave. Okay? That means that we have 32 gigabit per second recorders at each station. That's one high-definition movie every second. It's literally a ton of data. The hard drives that we use for M87 took up about half a ton. 40,000 lifetime selfie budgets. I don't take selfies, but I'm told by people who do. 40,000 people's lifetime budget is about the amount of data that we took for M87. So it's fundamentally big data science. You see this room here, each of these blocks is 8 12 terabyte hard drives. And we just have shelf after shelf after shelf of them. It's also high precision science because in order to time tag everything so we get the ups and the downs and the wiggles in those radio waves, we need atomic clock precision at every site. So we need to deploy masers to each location. And what the Event Horizon Telescope is formally is a collection of sites, existing facilities that have been outfitted with the special recorders, the special timing standards around the world, and this set of facilities to complete that process and produce the data at focus, and then image that data and interpret it. It literally is going back to the ends of the Earth, all the way to the South Pole, Chile, Hawaii, Spain, North America. And it's not something that we didn't think would work. We've been doing this for a long time. This is a slide you're not supposed to read, just point out that 2007 was the first time we tried to do one of these experiments. What changed recently is we finally had enough telescopes to make a picture, but we knew this would work, and we knew something would be there to see. So what should it look like? There's really two physical effects that matter qualitatively. If you want to make quantitatively correct pictures, there's a lot of details. But if you just want to understand the large scale structure of the image and why it looks that way, there's really only two pieces of physics that you need to understand. The first is gravity, and it's that gravitational lensing. But not as Eddington was looking for it, because now we have photons passing very close to the event horizon, and in some cases they will whirl about before coming to us. The net result of the bending of light around the black hole is that it leaves a shadow. It leaves an empty region in the middle. It's quite literally the image of the event horizon. What would fill in that region would be photons that would have had to go through the black hole back out to us, which they cannot do. I should point out that this is a democratic shadow. Okay, it doesn't depend on where you are. Everybody in the universe sees it. Okay, everybody gets a shadow. Right? It's not like we're aligned in a special direction. It's also purely gravitational. It's just determined by how photons fall around black holes. The second piece of physics you have to understand is what happens to moving sources that emit, moving light bulbs. And there's two elements that we have to worry about. The first is the Doppler shift. If we imagine a light bulb standing still and we look at it the left and the right, it looks the same color. But as soon as we start to move it at high velocity, the people who have the light bulb coming towards them see it bluer, and the people who see the light bulb moving away from them see it redder. This is just the Doppler shift. The second, and much more importantly, is Doppler beaming. This is a question about what direction do photons go from a moving source. If the source is stationary, all the photons are going out equally in every direction, but as soon as I start to move the light bulb, the photons begin to beam into the direction of motion. The faster I move it, the more beaming there is. Okay? This is a purely kinematic effect. It's almost literally exactly what would happen if I imagined throwing things out of my car in every direction. If you saw me barreling down the if you saw me at rest on the 401, like we so often are, you see it in every direction. If I'm barreling down the 407, okay, you see it all moving at 120 kilometers per hour in the direction I'm going. It's the same effect. Okay? The net result of that is that moving matter produces these searchlights. They're bright in the direction they're moving. They're dim in the other directions. So now we can combine those two pictures with an idea of what it is that's producing the emission at the centers of galaxies. Here's a theoretical picture of what that might look like. We have a black hole at the center. We have these swirling gas flows as gas is rushing headlong down towards the event horizon. And those gas flows drag in large magnetic fields that twist up near the horizon and launch relativistic outflows, material that's not going in towards the black hole, but somehow is accelerated to near light speed away from the black hole. So this is our theoretical picture of what we think the structure of the stuff around the black hole looks like, the emission region. I should point out that that's not just a matter of theory. We have a lot of reasons to think that that's fact. Here's a picture of Centaurus A. It's a galaxy that looks very similar to ours. All of the individual stars you see are actually in our galaxy. The stars from Centaurus A is that milky white haze. You can't see the individual stars, it's too far away. You see the gas lanes, that's the dark stuff. We're seeing this galaxy nearly edge on. And if you were to swap out your optical eyes for radio eyes, all of a sudden you'd see something else. You'd see these outflows above and below the plane. These are these jets that you saw in that prior animation. They're not without consequence. They help shape the visible universe. Here's a picture of not a galaxy, but a cluster of galaxies, a collection of many galaxies. Every white blob you see is a galaxy in its own right. The blue gas, the blue diffuse emission you see is hot X-ray emitting gas. Okay, it's actually an X-ray image. It's that gas that rains down onto the galaxies that ultimately gets turned into stars. And in red, you see radio remnants from jets in days past. And they've carved holes in that blue gas. They're shaping the galaxy cluster. They're ruling the fates of all the galaxies in them. So through these jets, they're not just incidental, they're not just paradoxical, something going out when it should go in. They're not just extreme, very relativistic. They also extend the influence of the black hole from the scale of the horizon all the way out to the scale of the cosmos. If we look at that jet not on scales of galaxy clusters, but on scales of the horizon, the picture might look like this. So the thing in the center is that shadow from gravitational lensing. It has a bright side because down near the base, everything is rotating around, and there's one side that's coming towards you like a merry-go-round, and one side that's going away from you. And there's the dim side, and that's the side that's not coming towards you. Now you can make this calculation more and more sophisticated, and the most sophisticated versions we have now are solving the equations that we think governs how gas swirls about and ultimately falls onto or flies away from black holes. Equations of general relativistic magnetohydrodynamics. It's a long name, so you know it's complicated. And it's solved on the biggest computers that we have, and then we go through the process of making pictures out of that, and they look the same. There's a shadow, there's a bright side, there's a dim side. And that just comes from gravitational lensing and light in motion. So what did we actually see? So I'm going to take us on a tour, and that tour is going to begin with the night sky as seen from around here. This was actually done in Waterloo. Because Waterloo is frequently overcast, as it is today, I use stellarium. I'm also a theorist, so that seems fitting. I do a lot of my work on computers. We were focused on M87. The M for M87 comes from Charles Messier. Charles Messier was an 18th century comet hunter. That's what you did back then to become famous. You go find comets. Of course, everybody wanted to find comets. So the way you found a comet is you scanned the sky and you saw fuzzy, dim patches that weren't there the night before. Because by the time you saw a beautiful comet that had twin tails, everyone else had also seen it, right? So if you wanted to be the guy who got to name it, you had to catch them early. And Charles Messier made a catalog of more than 100 objects that were fuzzy patches that were not comets. This was his "These will not bring you fame and fortune, ignore them" catalog. Okay? His "Don't look at these objects" catalog. Of course, astronomers now look at these all the time. So this one man's "Don't look at these for fame and fortune" is another person's gold mine. So we're looking at Messier's 87th not comet. And that lives in the constellation Virgo. And we're going to step forward one frame at a time so that you can see in every prior frame how much we've zoomed in. Okay? We zoom in twice. Now we're not in stellarium. Now we're actually looking at real pictures. You can see that Virgo is not home to a single galaxy. It's home to one of these clusters of galaxies. The Virgo supercluster is comprised of more than 2,000 galaxies all orbiting each other. The brightest galaxy within the bunch is Messier's 87th not comet, M87. And at this point, we can start to see it has a funny feature on it. That's not a camera artifact. That's real. That's one of these jets. This is an iconic Hubble image that shows this jet over thousands of light years. It is also the highest resolution optical image that we have of this. To go any further, we need to trade in our optical eyes for our radio eyes. And here's a picture from something called the Very Large Array, the VLA in Socorro, New Mexico. In many respects, it's very similar to the Event Horizon Telescope. It is not a single instrument, but a collection of many radio dishes that fill in shards of a mirror in almost exactly the same way. So how do we get from images, or get from shards of data to images? How do we go from this horrifically scratched up optical element to making beautiful pictures? There's two strategies that you might follow. The first is know what the scratches are doing and try to undo it. That's deconvolution. There are tried and true methods for doing this that people have been using for 40 years. Another way you might do this is something we call regularized maximum likelihood methods. These try to fit the image, but get to impose restrictions on what kinds of images are reasonable. An obvious restriction is it better be positive definite. What do I mean by that? There's nothing blacker than black. There's no negative intensity in your image. Okay? That's free. That's true. You have light or you don't have light. You don't have any places where you have less than zero light. But there are other things that might not be true. You might assume that it was smooth, or you might assume that it was sparse. The light is collected into as smaller regions as possible. Those don't have to be true. These are two fundamentally different methods. And you might worry about bias. If you were looking for fried chicken, you might be concerned if you were picking up labradoodles. Or if you were looking for blueberry muffins, you might be concerned if you found chihuahuas. So these are examples taken from my computer vision friends. It's really a statement of how do you know, after all of this extra computational reconstruction, that what we're seeing is what we think we saw? And the answer is, in part, redundancy. We had 4 different teams across the globe attempting to execute these tasks. 2 of these teams used the tried and true method. 2 of these teams used this more sophisticated but less well-tested, regularized maximum likelihood method. They were separated literally by global distances. We had representatives on nearly every continent. And we would do things like make simulated data sets from images where we knew what the truth was. And we would give it to them without telling them the truth and ask them to reproduce it. And sometimes these were crazy. My favorite was the snowman test. We gave everybody images or data taken from a truth image that was a snowman. And we didn't tell them it wasn't real. We said, well, here's something, you should be able to reconstruct it, what do you see? And then it became a point of pride, who got the buttons, right? Because you could actually see the coal buttons down the center of the snowman in some of the pictures. But for the paper for M87, we looked at things that might be more appropriate. The first would be rings and not rings. Or rings and ring-like, sorry. So the top is the truth image. This is the pictures from which the data was taken. The 2 teams who were using the tried and true methods reconstructed that, and the other 2 teams that used these newfangled methods reconstructed that. And you can see that where they saw rings, they got rings. Where they saw crescents, something where the ring was bright on one side, they recovered crescents. And I preempted not rings. More important, perhaps, than being able to tell that you saw a ring is being able to tell when you didn't. So there's data taken from a disk and data taken from a double point source. These are 2 things that might show up repeatedly in astronomy. And again, all teams did well there. And of course, you can try actual astrophysical simulations and ask how well people did. So these are the kinds of pictures that give us some confidence that this process produced reasonable pictures. And this is very similar to how the VLA produced that picture of M87. In fact, they used exactly the first option, the tried and true method. Okay, so to continue our zoom in, now that we understand where these radio images are coming from, we're looking at the very large array again, but this time at a shorter wavelength, means higher resolution. Now we've had to give up the VLA and we've had to go to an Earth-sized radio telescope. The EHT is not the first such telescope, but it is the shortest wavelength. This image was taken at a wavelength that's almost 200 times that of the EHTs. Again, Earth-sized telescope, shorter wavelength, even shorter. Same wavelength, but for longer, higher sensitivity. You can start to see in this picture something interesting. There's not only the jet that you saw in the optical, but there's also a piece on the other side. We don't see it very clearly because of exactly this light in motion, this beaming effect. In M87, the jet is coming towards us, which means the jet on the other side is going away from us, and the light it emits is beamed away, so it looks dim. And then here, this is the highest resolution image of M87 ever published up to April 9th. And on April 10th, I should point out that this is a zoom in, if you weren't keeping track now, of a factor of 70 million. Okay, so that's the magic of exponential growth, right? By shrinking by about a quarter or a third every frame, after about 12 frames, we've really made some progress. Here's the picture the EHT released on April 10th. One of the reasons to show this is to answer the question, why is it so blurry? Well, we did make a quantum leap in resolution. We still only have a few resolution elements across the image. We're working on it. Okay, but this was not just a little bit higher resolution, but a lot than the next highest resolution image. So what does that mean? Well, first, what could it have been? All right, the shape of this image is in many ways dictated by gravity. That shadow shape is dictated purely by gravity. Okay, general relativity makes a prediction for that. But it could be something different if gravity were wrong, if general relativity were wrong. If black holes were not the objects that Karl Schwartshield and later Roy Kerr said had to exist in Einstein's general relativity. If your black holes came more in the peanut M&M variety, or even the classic M&M variety instead of the, Whopper variety, pick your favorite spherical candy. The shape of that could be wrong, the size could be wrong. It could have multiple pieces. It could, in fact, not be a single object. We didn't see any of that. Is it really a black hole silhouette? So we're sure we saw a ring, but are we sure that we understand what the ring really is? The answer to that is really the answer to the following 4 questions. How big is the ring? How thick is the ring? How dark is the interior? How sharp is the transition? And to answer that, we wouldn't actually look at an image. We didn't look at an image. We constructed other analyses based on geometric masks. And they allow us to quantify how big, thick, dark, and sharp the image is. And it's worth pointing out, something I've grown fond of saying, is that all of science is error, the rest is opinion. And what do I mean by that? I mean, making a measurement is easy. Knowing how well you've made it is what's really hard. And most of the work that we did in the analysis was not to figure out that it was 42 microarc seconds in diameter. It was to figure out that we knew that plus or minus 1 microarc second. And that allowed us to make statements about how much confidence we had that this was actually a photon ring, actually the shadow of a black hole. You might ask, what about that nice, sophisticated, general relativistic magnetohydrodynamic simulation? How right is that picture? After all, some of the story I told you about why the picture looks the way it does comes from assuming something about the underlying emission region dynamics. Unfortunately, weather is a problem, just like it is on Earth. If I showed you a picture of a cloud and I asked you which one of the mugshots rained on you, you might have a hard time, because none of the clouds in the library look exactly like that cloud. There are some things that look a lot more like that cloud, but none of them are exactly the same. Small turbulent motions in the air around the cloud change its shape. And so we need a way to compare these. The same problems happen when we look at numerical simulations, when we look at those GRMHD simulations. We have to deal with the weather. Here's a panel that shows a large number of them, but even still a subset. The Event Horizon Telescope collaboration produced the largest library of these sorts of simulations ever produced, requiring supercomputers across the world, operating for months. And what we get are these weather-laden movies, small structures that are driven by random events, just like the shape of our clouds. And we need some way of determining how exactly these are similar. The answer is to use these movies to assess how much variability we have. And one of the key results of the Event Horizon Telescope was that, in fact, most of these movies are consistent within the bounds of the uncertainty in the measurement of the data and the uncertainty imposed by the weather in the simulation, the turbulent fluctuations in the simulations themselves. So here I'm showing in the center a frame from a simulation. And on one side, I'm showing you the image. And on the other side, I'm showing you an image reconstructed from that simulation. I'm not going to tell you which one's which. They're consistent with each other. So this picture that we've been presenting, these bedtime stories we've been telling our graduate students for decades now about how those jets are launched, seem to work all the way down to the event horizon. You might think about just slapping a ruler on the image. I was told that this was not sufficiently scientific, so we did something a little bit more sophisticated, but it's the same thing. You take the image with all of the details that go into making that image and measure the size of the ring. Extract information about size, width, etc. One of the key results that came from all of this was that we have 3 different ways of measuring features on that image, features in the emission region of M87, the size of that ring. And those 3 different ways produce my second favorite picture in the first 6 publications describing the first science results from the Event Horizon Telescope. Second favorite picture after the first image. And it's so boring. It's wonderful. Because all of these methods applied independently with their own different peculiarities, applied on 4 different days, because we didn't just observe M87 once, we observed it 4 different times. And we observed it in 2 different frequencies, very close together. And so in all of those 8 data sets, it turned out we got the same answer for each of those different methods. And that answer was a 6.5 billion solar mass black hole, an object that's not a little bit more massive than the sun, but billions of times more massive. And it was consistent. And it was consistent with a prior measurement. And that was really interesting. Because our 6.5 billion solar masses comes from the dynamics of light down near the event horizon, how much light is bending around. The other measurement came from the dynamics of stars, not at the event horizon, but out at distances of 60 light years. So astronomically, that's still pretty close. But practically, that's vastly further. It's 100,000 times further away. Our photons are 40 light hours from the black hole. Those stars, 60 light years. And both of these methods produce an estimate for the mass. These estimates are consistent with each other. So one 6.5, the other 6.1, but they both have a range of 1. And so they really are consistent with each other. And what knits them together is our understanding of gravity. What sets the dynamics of the stars is Newton's theory of gravity, which is a limit of general relativity far away. It's the same thing. And Einstein's theory of gravity down near the horizon. And so in an important way, this produces a key test of general relativity. There's also a comparison with longer wavelength observations. Here's that 3 millimeter observation. And one thing that you can see very clearly in the 3 millimeter observation is the extended direction of the jet, that large scale feature that we saw even in the optical images. And these images are aligned the same way. You'll note that this image is bright on the bottom, not bright in the direction of the jet. But it turns out that that asymmetry is exactly what was predicted. It's predicted by those twisting helical motions down near the black hole, down near the horizon. So this provides, I think, the first empirical support that not only do those bedtime stories we tell our graduate students, is consistent, but in fact, key pieces of it, the idea that these jets are launched by large-scale electromagnetic fields being twisted around black holes, are in fact true. It also means that we can begin to answer some of the most foreboding questions about black holes. Do monsters really exist? Are there really event horizons? Right? Are there places in the universe that you can go into and never come back out of? And the answer is yes. The argument is a little involved. It involves the distinction between meteors and meteorites. Right? So a meteor is a piece of space rock ramming into our atmosphere, heats up and shines. We see this in meteor showers. Meteorite is when it gets down to the Earth. All of the kinetic energy it has after plowing through the atmosphere goes into creating this impact crater. Okay, so here's one, I think, in Arizona. All right, so this is what I would call accretion luminosity from the meteor hitting the atmosphere, impact luminosity from the meteor getting all the way down to the surface. The same thing happens around black holes. Black holes will have accretion luminosity, but there's no impact luminosity because there's no surface. The material goes through into the horizon, and it's gone forever. It adds to the black hole. But if I were to take that black hole and replace it with a star, replace it with something with a surface, then I would get that impact component. And I can look for that. I can search for that. And because now I have this picture that I believe, I understand how to do that process or how to do that search. Now, that impact luminosity doesn't come out in the millimeter. It comes out in the infrared. It turns out that for an object like M87 with its size, that infrared and even optical photons are the peak of that impact luminosity. And so this requires a combination, a synthesis, not only of the millimeter constraints on the size, how big that shadow is, millimeter constraints on the fundamental picture for how black holes are interacting with the stuff around them, but also infrared and optical measurements of the flux. The prediction of that impact luminosity is that green curve, and the data is that black and red points. It's all vastly below. We don't see the impact luminosity. We see matter going in. We don't see anything coming back out. Horizons do seem to exist. And they're everywhere. M87 is a prototypical example of something we call an active galactic nucleus, but we see these across the night sky. Here's a picture in gamma rays, what you'd see if you had gamma ray goggles. And every little circle points to or indicates the location of an object like M87. In fact, this is a highly specialized subset of these objects because these are ones that have jets, and these jets are all pointed directly at us. And so for every circle you see, there's something like 10,000 other objects that you don't see in the universe. And what we've learned about M87 and the relationship of the black hole to the surrounding material, we now think we know about all of these as well. And black holes now come in many sizes. I mentioned early on the stellar mass variety. People are looking at those now not only in X-ray binaries, but they look at them with with LIGO, with gravitational wave observations, a new branch of astronomy where you study the universe not in light, but in subtle ripples in the structure of space-time. And between LIGO and the Event Horizon Telescope, we now have black holes that span 8 orders of magnitude in size. And they all seem to be described by the same underlying structure, It's again a prediction of general relativity, which didn't have to be true. It's kind of like saying your house is a scaled up version of a shoebox. Of course, it's not true. But for black holes, that is true. Even though it's 100 million times more massive, it's the same fundamental object. So what's coming up? We're doing this now again for the black hole at the center of the Milky Way. We didn't just look at M87 in 2017. We also looked at a number of other objects, and we're getting through and analyzing and interpreting those. The one at the center of the Milky Way is very different. This picture shows not a dot that shows you where it is, but that's an actual image of the black hole at the center of the Milky Way at the similar wavelength of the VLA image of M87 we saw. The gray bar indicates the same distance in Schwartshield radii, the same distance in black hole radius, half black hole diameters. If Sagittarius star and M87 were the same sort of thing, we would know they're not. We'll also look in polarization. We'll look in different wavelengths. And we'll begin to make the first images that move. This is a fundamental necessity for the black hole at the center of our galaxy, which is moving on timescales of tens of minutes. And let me just take a last couple minutes to reflect on, I think, the past year, because this has been extraordinary to many of us. So as a theorist, I often make predictions, but sometimes I make predictions to our PR staff, and I told them many years ago we'd be on the front covers of newspapers, so I was very happy to see that. I said front covers of textbooks. That's already happened. I'm not used to things happening so fast. I didn't foresee the memes. They're probably better. In fact, the first tweet I saw was a Brexit tweet with our image, so I didn't even see a congratulatory tweet, I just saw Brexit. Sauron, people did notice the alarming similarities between our image and donuts. Before we released our picture, some people in our collaboration put a simulated image that looked quite similar to our picture into Google's image search, and they got back fire donut ring. It's like, yes, okay, that sounds right. I think I first realized the impact when we became the Google CAPTCHA, so that was fun. So we made Google disappear. But more seriously, one of the wonderful things about this picture is that it's easy to understand. It's easy to understand in the sense that it's visual, so you don't have to be an expert, you just have to be curious. And it looks like a black hole should look. It's black, it's a hole. Okay? It's also laden with physics and gives me an opportunity to stand before you and talk to you for an hour about what the heck this is. It's an amazing tool for connecting people about science. And now this picture has been seen not just by a handful of scientists and people who come to public lectures, but the European Southern Observatory estimates by 4 billion people. So this image no longer belongs to the EHT, it belongs to the world. It's part of all of us. And that's especially important, I think, in light of the fact that projects like the EHT are only possible when you get large numbers of excellent people together. The EHT doesn't belong to one person, and I'm very proud to be part of a large team. There's more than 347 people on those first papers. A large fraction of them are shown in this picture, and we populate countries all over the world and are on almost all the continents of the world. Ironically, I think we're missing Australia. We have Antarctica covered. That's the hard one. I don't know how a radio astronomy experiment doesn't manage to have an Australian, but we really are a global collaboration because you need a global collaboration to build an Earth-sized telescope. More than that, we're a collaboration that does include physicists, astronomers, and engineers with a wide variety of cultures. And we're more than that, and I think at a facility like this, it's worth pointing out. We all have families and institutions and funding agencies that made what we did possible. And without that community support, nothing that we talked about today could have happened. And so having community supports and community centers, community events, I think is critical to making everything happen, even things like this. Thank you.